A tiny glass cell filled with rubidium atoms, smaller than your fist, just became one of the most consequential pieces of military technology developed in decades. Scientists at the United States Army Research Laboratory published a breakthrough in June 2026 that could fundamentally change how every soldier on a future battlefield sees, communicates, and survives. And the physics behind it reaches straight into one of the strangest corners of quantum mechanics, a place where atoms behave less like matter and more like antennas tuned to the entire universe. This is the real science behind the quantum breakthrough that could reshape American defense, and why the race to own this technology is already changing the strategic balance of power between the world's largest militaries. To understand why this matters, you need to understand what every modern military actually runs on. Not bullets, not fuel, though those matter too. Modern warfare runs on signals. Every drone, every radio, every encrypted communication between a command post and a unit in the field, every radar pulse searching for incoming aircraft, every GPS coordinate guiding a precision strike, all of it is an electromagnetic signal. Radio waves move invisibly through the air, carrying information that can win or lose a battle depending on who can send it, receive it, hide it, or jam it most effectively. The side that controls the electromagnetic spectrum on a modern battlefield controls the fight. And for decades, the physical tools used to detect and analyze those signals have barely changed in their fundamental design. If you had no idea that a glass jar of atoms could outperform every antenna humanity has ever built, smash that like button right now, because what the Army just demonstrated changes the rules of that entire game. The breakthrough centers on something called a Rydberg quantum sensor, built around a physical phenomenon that sits at the very edge of what quantum mechanics allows atoms to do. Normally, the electrons orbiting an atom stay close to the nucleus, occupying low energy levels and interacting very weakly with the electromagnetic environment around them. But when you hit certain atoms with precisely tuned laser light, you can push an electron up to an extraordinarily high energy level, thousands of times farther from the nucleus than it normally sits, while keeping it still technically bound to the atom. Physicists call these configurations Rydberg states, named after Swedish physicist Johannes Rydberg, and the atoms that reach them are called Rydberg atoms. In this excited state, the electron's orbit becomes so enormous that the atom itself essentially becomes a giant, exquisitely sensitive antenna, reacting to even the faintest passing electromagnetic field in ways no conventional device can match. What the Army Research Laboratory team at DevCom did for the first time in history was use these Rydberg atoms, not just to detect a radio frequency signal, but to measure the full three-dimensional direction of that signal simultaneously. Not just whether a signal exists, not just how strong it is, but exactly where it is coming from, in 3 complete spatial dimensions with an angular accuracy of roughly 2 degrees. Research physicist David Meyer, who led the team, described this capability plainly, saying the modern battlefield is an extremely complicated radio frequency environment with hundreds of distinct signal sources filling the spectrum at any given moment, and that having a single platform capable of covering the entire radio frequency range while measuring the full, 3-dimensional direction of incoming fields represents a potentially transformative capability, especially for what the military calls spectrum awareness. Subscribe now if you're starting to understand why knowing the exact direction of every signal on a battlefield could change the outcome of a conflict before a single shot is fired. Here is what makes this sensor genuinely revolutionary compared to everything that came before it. Traditional antennas have a fundamental physical constraint baked into their design. To effectively detect a radio wave of a particular wavelength, a conventional antenna generally needs to be physically sized in proportion to that wavelength. A very long wavelength, which means a low-frequency signal, requires a long antenna. This creates unavoidable trade-offs in military hardware, where engineers must choose which frequency ranges to cover at the cost of not covering others, leading to bulky, specialized equipment that can only do one thing well. ARL's Rydberg quantum sensor breaks this relationship entirely. The rubidium vapor cell at its core is just a few centimeters across, far smaller than the wavelengths of most radio signals it can detect. Yet because its sensitivity comes from quantum mechanical properties of the atoms themselves, rather than from any physical sizing relationship, it can operate across the entire radio frequency spectrum, from direct current all the way up to terahertz frequencies, in a single compact package. Like and subscribe if wrapping your head around an antenna the size of a walnut that covers every radio frequency ever used by a military is the kind of physics breakthrough that this channel exists to explain. The physical mechanism behind this is elegant in a way that textbooks rarely capture. Inside the glass cell, rubidium atoms float in a vapor at extremely low pressure. A pair of precisely tuned lasers shine through the cell, one locking the atoms into an intermediate energy state, and a second pushing the electrons up, into the Rydberg configuration. In that highly excited state, the electron cloud surrounding each atom becomes so large and so loosely bound that even an incredibly faint passing radio wave causes a measurable shift in the energy levels of the atom, which, in turn, measurements of the incoming electromagnetic field, its strength, its polarization, and now, for the first time, its complete three-dimensional direction of travel, known in physics as the k-vector. This matters enormously for military applications, specifically because of what the k-vector tells you. If you know a signal's strength, you know something is transmitting. If you also know its frequency, you can roughly identify what kind of system is transmitting it. But if you know its exact three-dimensional propagation direction, you now know with precision where that transmission is coming from, turning a passive sensor into a real-time passive geolocation system that requires no active emissions of its own, meaning it cannot be detected or targeted by an adversary searching for active radar or antenna systems. A sensor that listens, without announcing itself, covers every frequency simultaneously and pinpoints the direction of every signal it detects, represents a qualitative leap in what a single soldier or a small unit can understand about their electromagnetic environment in real time. The implications for electronic warfare are staggering, and they extend in every direction across a modern battlefield. Electronic warfare today involves three overlapping activities: sensing the electromagnetic environment, exploiting signals for intelligence, and attacking adversary communications through jamming, or become dramatically more capable when your sensing platform can cover more spectrum more precisely in a smaller and harder to detect package. An enemy unit using radio communications could theoretically be located passively without the locating force, emitting any detectable signal themselves. An adversary drone swarm communicating through encrypted radio links could be mapped in real time as it approaches. An enemy jamming system trying to blind friendly communications could be pinpointed and targeted before it succeeds. This capability also has profound implications for something the military calls counter-drone operations, one of the most urgent tactical challenges to emerge from recent conventional conflicts. Modern small drones communicate with controllers through radio signals that conventional detection systems often struggle to isolate cleanly, especially when dozens or hundreds of drones are operating simultaneously in a dense electromagnetic environment. Conventional counter-drone systems typically rely on radar to physically detect the drone's body in flight, radio frequency scanners to detect its communications, or optical sensors to visually identify it, and all three of these approaches have well-known vulnerabilities. Radar systems require active emissions that can be detected and avoided. RF scanners are often limited to specific frequency bands or require prior knowledge of what communications protocol the drone is using. Optical sensors depend on line of sight and are easily defeated by darkness, weather, or simple camouflage. The Rydberg sensor's ability to cover the full frequency spectrum simultaneously while resolving the three-dimensional propagation direction of any detected signal creates a passive, broadband direction-finding capability that requires no prior knowledge of what frequency the drone is using and no active emissions that could reveal the sensor's own position on a battlefield where autonomous drone systems are proliferating faster than the defensive technologies designed to stop them. That combination of properties is precisely what military planners have been describing as the capability gap they most urgently need to close. If the idea that a jar of quantum atoms might be the best answer to the drone threat of modern warfare sounds like something straight out of a science fiction novel, make sure you subscribe, because the physics behind that statement is completely real. The Army's investment in this technology did not happen overnight, and understanding how it arrived here matters for understanding where it goes next. DEVCOM's Army Research Laboratory has been investing in quantum sensing research since the early 1990s, building internal expertise in quantum physics at a time when most of the applications seemed far too theoretical to interest most defense planners. In 2024, the same team published results demonstrating the sensor's ability to measure radio, frequency polarization, and even decode information that had been encoded in that polarization, a separate and equally significant capability for signals intelligence work. In 2023, ARL was formally designated as one of only 4 Army Quantum Information Science Research Centers, cementing its role as the primary node in the Army's quantum technology ecosystem. The 2026 K-vector measurement result, published in the peer-reviewed journal Physical Review Applied, is the product of that continuous, patient, decades-long investment finally clearing a threshold nobody had cleared before. But the United States is not pursuing this alone, and that context matters enormously for understanding the urgency behind the program. China has declared quantum technology a national strategic priority, embedding it explicitly in its 5-year plan and pouring state resources into quantum sensing, quantum communications, and quantum computing programs simultaneously. Chinese state investment in quantum research is estimated by multiple independent analysts to rival or exceed American public investment in the field, and it is backed by a coordinated national strategy that integrates civilian academic research, state-owned defense enterprises, and military R&D programs in ways that the more fragmented American funding ecosystem does not naturally replicate. Chinese researchers have published peer-reviewed results in quantum sensing that rival, and in some areas have preceded, comparable American milestones, including demonstrations of satellite-based quantum key distribution, where quantum mechanics itself is used to guarantee that any eavesdropping on a communication channel is mathematically detectable, a capability the United States has not yet fielded at operational scale. Russia unveiled a 50-qubit quantum computing prototype in 2025, a more modest capability than leading American and European systems, but a clear signal that Russian quantum investment has survived the economic pressures of the past several years. Europe has established dedicated quantum defense research programs through its defense industrial and space initiatives, with several member states running independent national quantum programs alongside the EU-level effort. The race to translate quantum physics into fielded military capability is global, well-funded, and accelerating simultaneously on multiple continents. And the nation that successfully fields quantum sensing, quantum-secured communications, and eventually quantum computing advantages will hold a military edge that conventional technology investment alone cannot replicate or close. Like and subscribe if you are only now beginning to understand why defense analysts describe the quantum race as the most consequential technology competition of the next 2 decades. There's a second major quantum defense frontier running parallel to the sensing work at ARL, one that carries even higher strategic stakes over the longer term, and that is quantum computing's implications for cryptography. Every piece of encrypted military communication, every classified database, every secure satellite uplink depends on mathematical encryption algorithms whose security rests on one simple assumption: that no classical computer could ever factor the enormous prime numbers underlying the encryption keys in any useful amount of time. A sufficiently powerful quantum computer running an algorithm called Shor's algorithm could theoretically break the most widely used public key encryption systems, not in centuries, but potentially in hours or days. That single capability would render decades of encrypted military communications retroactively readable to any adversary who had been, storing them while waiting for quantum computing hardware to mature, a threat intelligence professionals call harvest now, decrypt later. If you are only now realizing that foreign intelligence services may already be storing encrypted American military traffic specifically to decrypt it once quantum computers become powerful enough, that is not a theoretical concern. It is an acknowledged, documented part of the strategic planning discussions happening right now inside the Pentagon. The National Institute of Standards and Technology finalized its first set of post-quantum cryptography standards in 2024. Algorithms specifically designed to resist attacks from quantum computers, and the military transition to those new cryptographic standards is an ongoing, complex, and expensive program that spans every branch of service and every classification level simultaneously. The timeline pressure on that transition comes directly from the uncertainty about when adversary quantum computing capabilities might reach a level capable of threatening current encryption. And that uncertainty is itself a function of how fast the underlying hardware matures, which nobody can currently predict with precision. It is worth being honest about where the limits of quantum computing for defense currently sit, because overstating quantum capability is one of the most common failures in science reporting about defense technology. The Army's own senior leadership, responding to a Department of Defense Inspector General review published in January 2026, acknowledged an internal Pentagon consensus that demonstrable quantum computing capabilities applicable to real military operations remain roughly 10 to 15 years away from readiness. The Inspector General's review itself found that the Pentagon had not consistently updated its assessments of which specific military problems quantum computers could realistically address in the near term, creating strategic uncertainty about timelines and investment priorities across the Army, Navy, and Air Force simultaneously. Quantum sensing, however, sits on a significantly shorter timeline than quantum computing, precisely because it exploits quantum mechanical properties of atoms without requiring the error-corrected qubit systems that make quantum computing so difficult to scale. The Rydberg sensor does not need to maintain fragile quantum coherence across thousands of entangled qubits. It needs to maintain individual atoms in well-controlled, excited states long enough to take a measurement, a far less demanding requirement that the ARL team has now demonstrated in a working physical system, not just a theoretical model. That distinction matters enormously for anyone trying to assess how quickly this technology moves from a laboratory in Adelphi, Maryland, into actual hardware carried by soldiers in the field. The path from laboratory demonstration to fielded military hardware involves substantial additional engineering, and understanding that path honestly matters. The current sensor requires laser systems to create and maintain the Rydberg atomic states, and those laser systems are themselves precision instruments that add size, power requirements, and maintenance complexity to the overall package. Miniaturizing those lasers, hardening the entire sensor assembly against the vibration, temperature extremes, and rough handling of actual battlefield conditions, and integrating the sensor's outputs into existing military command and control software architectures are all substantial engineering challenges that remain ahead. None of this is a reason to dismiss the significance of the breakthrough. It is simply an honest accounting of the distance between a peer-reviewed physics paper and a piece of hardware in a soldier's kit. What the June 2026 result definitively established is that the fundamental physics barrier has been cleared. The question of whether a quantum sensor built on Rydberg atoms could measure full three-dimensional electromagnetic field direction has now been answered with a resounding yes in a working experimental system under controlled conditions with results rigorous enough to survive peer review at one of the world's leading physics journals. Every subsequent engineering challenge is a problem of implementation rather than a problem of physical possibility. And that is exactly the distinction that justifies the sustained investment this program has received and is certain to receive in larger quantities going forward. The broader defense quantum ecosystem surrounding this breakthrough extends in multiple directions simultaneously. The same quantum sensing principles that make the Rydberg sensor so powerful for electromagnetic field detection also apply to navigation systems that operate without any GPS signal, using the quantum mechanical behavior of cold atoms in gravitational and inertial fields to track position and velocity with extraordinary precision even underground, underwater, or in GPS-denied environments where conventional navigation fails entirely. GPS jamming and spoofing have become standard tools in modern electronic warfare, used aggressively in multiple recent conflicts to blind opposing forces and deceive navigation systems. A quantum inertial navigation unit that requires no external signal of any kind to track its own position would be fundamentally immune to those attacks, since there is no incoming signal to jam or fake. Several defense research programs in the United States and allied nations are actively working toward compact quantum inertial sensors capable of providing continuous navigation accuracy comparable to GPS over extended periods, using precision measurements of atomic motion under gravity rather than satellite timing signals. Quantum gravity sensors offer a separate but equally significant military capability: the theoretical ability to detect underground tunnel networks, subterranean bunkers, concealed weapon storage facilities, or buried infrastructure from surface or airborne platforms, without drilling, without radar emissions, simply by reading the minute gravitational variations caused by density differences in the ground below. Existing military gravity sensing technology exists, but is too slow, too large, and too imprecise for tactical applications. Quantum gravimeters based on cold atom interferometry, which measure gravity with sensitivities many orders of magnitude greater than classical instruments, have already demonstrated laboratory performance that suggests eventual tactical applicability, and multiple defense research agencies on multiple continents are funding the miniaturization work required to move them out of the lab. Quantum clocks, already the most accurate timekeeping devices humanity has ever built, enable time synchronization precise enough to support entirely new generations of secure communication, electronic warfare, and navigation technology, whose performance is fundamentally limited by the accuracy of the timing references underlying them. The world's major militaries are not watching this from the sidelines. They are running parallel programs with similar goals, similar physics, and similar urgency, and the results of that competition will shape the battlefield long before a majority of the public understands what a Rydberg atom even is. Defense technology transitions rarely happen in a single dramatic moment. They happen as a long series of incremental laboratory results that quietly cross physical thresholds, followed by years of engineering work that transforms those results into hardware, followed eventually by the sudden jarring realization by adversaries that the strategic balance has already shifted in ways they cannot easily reverse. The first full three-dimensional electromagnetic field measurement by a quantum sensor, published in Physical Review Applied in June 2026, is one of those threshold crossings. It will not make tomorrow's headlines the way a weapons test or a political summit does, but the soldiers who carry its eventual descendants into the field, and the adversaries who will face what those soldiers can now sense without being seen, will understand its significance in a way that no press release could ever fully convey. A glass cell of rubidium vapor, a pair of precisely tuned lasers, and 30 years of patient quantum physics research just opened a door that conventional electronics cannot close. If understanding the real physics behind the military technology that will define the next generation of warfare was worth your time today, make sure you are subscribed before the next breakthrough changes the rules all over again.